Right. In this discussion, we will look at how to calculate work and power during exercise. So, my first question is, what is a calorie and how do we fuel exercise? Now, when we talk about exercise physiology or how much work we're doing or how hard an exercise was, we naturally go to the idea of how many calories were burned. It's something that you learn from a young age. You do a lot of work, you burn a lot of calories. You eat a lot of food, you're taking in a lot of calories. So, first off, what is a calorie? I just think of a calorie as a measure of fuel. Just like your car uses gasoline for energy to run, your body uses calories from food for energy to perform all its functions. From breathing, thinking, walking, exercising, they all burn calories. In its strictest sense, calorie is a measure of heat, how much heat or energy is needed to raise a liter of water, a degree Celsius. But in practical terms, it's an amount of energy, how much fuel you burned or how much fuel you need. Now, in this in this discussion, we'll talk about work. And in exercise science and in physics, work is roughly equal to caloric expenditure. If you want to know about how many calories you've burned or who's burned more calories, look at who's performed the most work, and I'll teach you what work is. But anytime you do work, that's when you generate force and move an object or do something that requires energy. So contracting your muscles requires work, the heart beating requires work and energy, the brain thinking, all of those processes, they perform cellular work, and those require energy. And we generally get our energy from food. I think you guys probably know this. We eat our foods, hopefully good foods, that have potential energy in them, right? You have some foods that are energy dense or calorie dense, like a Snickers bar is packed full of calories per gram of weight, whereas celery doesn't have a whole lot of calories or a lot of energy per celery stick, right? So we eat our food to get potential energy, and we're going to take the energy out of the food to help power our muscle contractions. But how are they linked? Well, we have this common form of energy called ATP or adenosine triphosphate. This is a molecule that has three phosphates on it, and it's what our bodies use for energy. Think of it as a battery. It's uh, there's we have potential energy in watermelon or in hamburgers, but your muscles can't really use or process a watermelon, right? So what happens is we get all the energy out of these foods to form ATP, and then we use that ATP to perform our muscle contraction. This ATP has a lot of energy in it, and as we go from ATP to perform work, we actually rip off a phosphate here, illustrated by part of the battery coming off. And now we're down just to two phosphates, adenosine diphosphate. So ATP is like a fully charged battery with three phosphates, and a DP is a partially discharged battery. We've lost some of the energy, we've used it to perform work. When we rip that phosphate off, it provides the energy for the muscle to contract, the heart to beat, or the brain to do its functions. Now, it would be really nice if we just had a ton of ATP in our bodies, but we don't. We actually only have enough ATP to power us and keep us alive for a couple of seconds. Instead of storing a ton of ATP, our bodies actually specialize in recycling ATP. And so that's what metabolism is about. When we eat that watermelon, banana, or hamburger, or spaghetti, or Snickers bar, we're not converting that Snickers bar into ATP. That's not what happens, actually. What happens is that we use the potential energy in that Snickers bar to power metabolism, where we shove the ADP and the phosphate back together to reform ATP. The Snickers bar does not become ATP. Your fatty acids do not become ATP. We burn these And in that burning process, which you'll learn all about in chemistry, physics, and physiology, in that burning process or metabolism, we have enough energy to put the phosphate back on. So we recycle our ATP. Now, so this is called metabolism. Sorry for these stray marks. What other key things do I need to show you on this? Uh, you're also most likely familiar that in addition to needing food for energy, we also are highly reliant upon oxygen for energy. The most efficient and sustainable way for us to recycle ADP back into ATP requires oxygen. We use the oxygen to help burn the calories in the food to recycle the ATP. So as you'll see in a minute, we can actually quantify how much work is being done by measuring how much oxygen is being used. Now, another thing is anytime we go and burn these foods or burn oxygen, we produce heat. Wow, what is that? So another way for us to measure how much work is being done is to measure how much heat is being produced. And that's where the word calorie comes from. It means heat. And in exercise physiology, we measure energy expenditure by calorimetry, or how much heat a body produces. Okay, we'll learn more about these as we go along. So, how much work a person does is roughly equivalent to the total caloric expenditure, how many calories or how much energy we've burned to do that exercise. But in physics and physiology, work has a very specific definition that allows us to and calculate how much work was done and compare from person to person or exercise to exercise. In terms of physics, work is equal to the force that you apply to an object times the distance that you move the object. Okay, and we'll work our way through this. So let's say that I got this 5 kilo dumbbell here, and I lift it up onto a table that's 2 meters high. So the force would be, let me make sure how I wrote this. Actually, let's pretend this is 10 kilos. We got two 5 kilogram things on there. So this is a 10 kilo weight. So we can calculate the force. Force is equal to mass times acceleration. So we got 10 kilograms here. And the acceleration that we care about on Earth for most things like weight-bearing activities is just gravity. And you'll learn more about these things in physics. You don't need to understand the exact numbers where they're coming from right now. But we can calculate the force. It's going to be determined by the mass for the most part. So we lift 10 kilo weight and then we lift it a distance of 2 meters. So we can multiply all this out and we get a measure of how much work was done, 196.2 joules. I'm not going to make you calculate these things. I just want you to understand the concept. What influences total work done? Let's say that we had a person lift, instead of 10 kilograms, 2 meters, let's say it was 4 meters. Okay, that would double the amount of work and roughly double the amount of calories that were expended lifting that weight. Now, like this isn't going to be hard. Let's say they lift a 20 kilogram weight, the 2 meters. It's also going to double the work compared to that first scenario. Okay, what if we stick with that 10 kilo weight and they lift it 2 meters, but now they do it 4 times? So they do 4 repetitions of that. They lift the weight up off the ground 4 times onto the table. So we have that 196 joules, but now you have 4 repetitions. And so now you're going to have an estimate somewhere around 800 joules, right? I'm just doing this math on my head. But by doing the reps, doing 4 reps, we're quadrupling the total amount of work. So work is the product of force and distance. And for the most part, Force is the weight of something that you're lifting. So let's say that you're walking up a hill or you're walking and you walk 2 miles, or yeah, we'll just say 2 miles. What is the force that we care about? It's actually your body mass, the mass that you have to lift off of the ground with each step. So if you weigh 50 or 60 kilos, we would put 60 kilograms in there. And then the acceleration here is still gravity. That is our main thing. So in terms of how many calories you burn going around the track, it's mostly determined by how far you walk and how much you weigh and how much you're lifting with each step. Okay. Now, there are other things that will influence how much work you perform during exercise. One, if you're like doing a weight-bearing exercise like running, walking, or cycling, the percent grade, how steep the hill is. If you're walking on flat ground at 2 miles per hour, that's a lot easier than walking on a steep hill at 2 miles per hour, right? How steep and how much vertical gain you gain in an exercise is strongly influential on the caloric expenditure. It costs a whole lot more calories to go uphill than it does flat or downhill. Another thing that influences how hard you work is air resistance. So if you're going really fast or it's a very windy day, this has happened to me on my bike. One day I was riding my bike. We went way uphill. Me and my friends were riding down Zion National Park and we rode uphill and it was pretty hard because we were going uphill. And then we turned around and we're excited for the downhill. We're like, this is going to be easy. And it should have been, but it was like winds of like 45 miles per hour. So I had to keep pedaling to go downhill. It was crazy. That air resistance has a big influence on how hard an exercise is or how many calories you burn. Another thing will be how much weight you're carrying. If you weigh 50 kilograms, but you're carrying a 25 kilogram backpack, you have to include that in your total amount of work. If you're cyclists spend thousands of dollars to get lighter and lighter bikes. The reason being is that's less weight that they have to push with each pedal, and so they perform less work per mile. They still go a mile, but since they only have to push 20 kilogram or 20 pounds instead of 40 pounds, it's a lot fewer calories and a lot easier. And then another thing that's super important is the efficiency of movement. If I run a mile, that's a lot different than crawling a mile. If I bike a mile, that's going to be a lot different than running a mile. You can compare roughly the same amount of calories if you walk a mile at 2 miles per hour, 4 miles per hour, or even run it. But walking versus biking or running versus biking, way different efficiencies of movement, and you're going to burn way fewer calories per mile, do less physical work per mile if you're on a bike versus walking. Now let's talk about this scenario. Let's say you're watching The World's Strongest Man on ESPN2 at like 10 p.m. at night because that's when World's Strongest Man is always on because there's nothing else on. And you got these two giant men that are lifting up these huge stones onto a pedestal. Let's figure out who did more work, who used more ATP, and who burned more calories. The first guy puts one stone, it's a 100-kilo stone on a pedestal that's 0.5 meters. So if we calculate work, remember work equals force times distance. Force is mass times acceleration. The main thing here is 100 kilograms of mass. And the acceleration would be gravity. The distance is 0.5. Okay, you can calculate that out. You don't have to make these calculations to get the right answer. Now, let's say we got another guy that just puts a 50-kilo weight on a pedestal that's 1 meter. The gravity is the same for each of these. So really we're looking at 100 kilograms times 0.5 or 50 kilograms times 1. And it comes out to the same. Even though one lifted a much heavier weight, the other did it a further distance, and the total work comes out to be roughly the same. Well, calculated is the same, and the total caloric expenditure is going to be roughly the same. Now, the reason for that is to generate a force and to move it, your muscle has to contract. And for every centimeter that your muscle moves, and for every newton of force that your muscle generates, it requires a certain amount of ATP. And so, in order to refuel that ATP, we have to burn a certain amount of fuel. So the caloric expenditure is roughly the same for a given amount of work. Let me emphasize this again. Work is roughly equal to how many calories you burn in an exercise. Now let's talk about next. So we can measure energy expenditure in physiology and exercise physiology with something called indirect calorimetry. There's something first called direct calorimetry, where we directly measure heat production during exercise. Anytime you do an exercise, you're producing heat, right? That heat comes from metabolism, like burning fats and carbs and all of that. And we can measure that heat and get an idea of how much energy was expended and how much work was performed. But it's kind of hard to do that, to measure heat production. So we have a much more practical way, which is called indirect calorimetry. We actually measure how much oxygen is being used. Remember, when you do work, you break down ATP, and to recycle that ATP, you burn oxygen and foods, and in the process, you form heat, water, carbon dioxide. So instead of measuring how much ATP is being broken down, we haven't figured a good way out how to do that, we can measure how much oxygen you're using. And that in turn will tell us how much work you have performed. So with this mask, what we have my friend Josh on here, where we have him exercising on a bike, and his exhaled breath, it goes down into a machine here, and we measure how much oxygen he's used. We know how much oxygen is in the air, and so we look at how much oxygen is in his exhaled breath, and we can tell what he's used. And we know that that oxygen that's disappeared has been used in metabolic ATP resynthesis to fuel work. So for roughly every liter of oxygen that you use equals about 5 calories. Now this is called kcals. When you look at the back of your nutrition labels, they're kilocalories, but they're labeled with a big capital C, kilocalories. But for layman, you would just say calories. So for every liter of oxygen that I use during an exercise, that's roughly 5 calories burned of food and other energy sources. When you exercise, if you're doing intense cycling exercise, he might be at 3 liters of oxygen per minute. So that would mean that he's burning 15 calories per minute. Now, let's talk about another scenario. Let's say that on one day you walk around a track in 15 minutes, and another day you're feeling a little tired, maybe a little lazier, and you walk around the track more slowly in 30 minutes. Doesn't make a difference on how many calories you burn or how much work is performed. One day you go twice as fast as the other. It certainly feels harder, your heart's pumping faster, but is the total work or the total caloric expenditure different? Let's look at it. The force on both days, the main factor would be your body mass and gravity. Now, your body mass hasn't changed, and gravity certainly hasn't changed. So the force is the same, and you go 1 mile each time. So, and you're doing the same efficiency of movement, right? You're walking. So if you walk a track in 15 minutes or in 30 minutes, it's going to be the same amount of work and the same amount of calories with a minimal difference. There might be a plus or minus 1 or 2 calories here or there, but it is extremely close. But if the work's the same, why does it feel so much harder when you go faster? If you go around a track in 5 minutes versus 15 minutes, it hurts a lot more, right? You're going for your PR, your fastest mile time. Your heart's beating, you're breathing very heavily. The total work is still the same, but what you're feeling is power. Power is how much work you do in a unit of time. So in this, you did you did that 1 mile and you did your body mass around 1 mile, but you did it in a faster time. All right, so that would mean if you go faster, that's a higher power output. If I lift 10 pounds once, I do it in 1 second, and another time I do it just in 3 seconds, the power output is much higher when I do it faster in that 1 second. Power is how much work you do for a given amount of time. And while total work influences how much ATP and how many calories you burn, power influences the strain on the metabolic systems, and it strongly influences where you get your calories. Now, in my little drawing down here, I just reference oxygen. We have actually three main ways of generating or recycling ATP. And you'll learn more about these in biology, physiology, biochemistry. When we talk about metabolism, there are three main ways. The one we've talked about so far is aerobic metabolism. That's where we break down carbohydrates and fats primarily. And with in the presence of oxygen, using oxygen, we can get a lot of energy out of it, a lot of ATP, but it's a long process that takes a long time. Now, our other ways are glycolysis. This is the breakdown of carbs without oxygen. This is the process that forms lactate, which you guys might have heard about in the past. Being anaerobic, it's not requiring oxygen. It's actually a shorter process. When you get to chemistry and you have to memorize these, you're going to want to memorize either ATP phosphocreatine or glycolysis. ATP phosphocreatine system is 1 step. Glycolysis is 10 steps. Anaerobic metabolism is many, many steps, depending on if it's carbs or fats, amino acids, you're looking at like 30 steps that you're going to have to memorize. And the number of steps influences how fast it happens. So glycolysis happens quickly. You're breaking down carbohydrates partially, and you get ATP out quickly and energy out quickly. Other system would be ATP phosphocreatine. Now you guys are probably thinking, well, is that creatine supplement? That's what the creatine supplement is trying to target there. And it does it with a little bit, some efficacy. You can supplement creatine. So these different ways of recycling ATP have their advantages. The advantage of aerobic metabolism is you don't get a lot of ATP per minute. So ATP per second will be power. But you can sustain aerobic metabolism for a long time. So actually, the total amount of work that you do with aerobic metabolism is huge. It's what we rely on for most of our activities in our daily life. If you stop having oxygen, you can't breathe in oxygen, you die, because aerobic metabolism is our sustainable source of ATP. Now, glycolysis and phosphocreatine, these anaerobic steps, they're much shorter, they're faster, so they can give you ATP in a short amount of seconds, but they don't last very long. They can't sustain exercise for a very long time. And so if you want to sprint ridiculously fast, like a 100-meter sprint, you're going to be primarily fueled by this ATP phosphocreatine system. That's where you're going to recycle your ATP. It's a one-step process. You can recycle that ATP very quickly so you can go through more muscle contractions and run very quickly. The problem is you only have a little bit of phosphocreatine stored, only enough to fuel you for like 30 seconds of maximum exercise. So it's not a very sustainable way. It can get you through explosive things, but not something you can sustain for a long time. Glycolysis, you break down carbohydrates partially and get half of the potential energy out. Well, not even half. You get a little of the potential energy out, but you get it very quickly so that it happens in a short amount of time. So it allows you to have a lot of ATP per second, but as you'll learn later in the semester, when you go through glycolysis, it pollutes the muscle with these things we call metabolites or breakdown products of metabolism. And that causes muscle fatigue. So you can't sustain that metabolic pathway for very long either. Kind of short story. So let's say I want to run this fast. If I want to run that fast, I need to go for my glycolysis. I have to have some, I'll have some aerobic metabolism going, but I need to go into my glycolytic pathway for recycling ATP. That's going to pollute my muscle and cause muscle fatigue, so I won't be able to sustain it for very long. If I want to run for a long time, I have to go at a lower power output that's in my aerobic metabolism. So if I'm running at this speed, let's say this is 3 miles per hour or 5 miles per hour, whatever it is, say I'm running at 5 miles per hour and it's in aerobic metabolism, I'll be able to go on for a long time because I'm aerobically fueled. I have lots of carbohydrates and fats stored, and you can go for a ridiculously long time. If I want to go this fast, let's say this power or this speed is like 15 mile per hour sprint, I'll only be able to do that for a few seconds. I can go that fast until my phosphocreatine runs out, and then I have to slow down to where I can be fueled by glycolysis. And then as soon as that causes fatigue, I have to slow down even more to aerobic metabolism. So aerobic metabolism forms the base of all of our energy production and our calories. Without oxygen, without aerobic metabolism, we die. It's extremely influential. We'll learn more as you go through more about exercise science and exercise physiology, about these processes, about the metabolic pathways. But the reason that when you exercise at a high power output that it feels harder is because you're putting more strain on your body. You're probably pushing yourself up towards these other metabolic systems that cause muscle fatigue. It's going to drive your heart rate up. And so you might do the same work, same amount of work if you walk around a track at 2 miles per hour versus 4 miles per hour. But if you're going 4 miles per hour, you're at a higher power output and you're going to be relying on these other metabolic pathways that cause muscle fatigue. Now, this is a sneak peek, but when you endurance train, what happens is you raise this line for aerobic metabolism up higher. So let's say that before training, if I ran this speed, that power output we'll say is 5 miles per hour. Before training, running 5 miles per hour, I had to fuel that all with glycolysis, which is going to cause fatigue, and I'm not going to be able to sustain it for very long. After training, this aerobic metabolism box increases, meaning you have more mitochondria, you have a bigger heart, more blood flow. And so now all of this power output at 5 miles per hour can be fueled aerobically, and you can go a lot longer. That's why we see huge increases in endurance with endurance training. We can shift to more sustainable metabolic pathways. Now, other ways to calculate power, I've showed you power is equal to work over time, but as you go forward in your studies, keep in mind that power is also, it's very easy to calculate as force times velocity. I generally like the force times velocity when I'm thinking about power output, lifting weights, like doing a squat or a bench press. So if I'm doing a squat, fast or slow, right? So the force is going to be, well, let's do bench press. That's a little easier to illustrate. So the bench press force is going to be the weight on there. So let's say I'm lifting 100 kilograms times gravity is going to be constant. As long as you're on Earth, it's going to be gravity. Now, so that's the total. And then the force. Now the velocity is how fast you're moving it and how far you move it. If you go up quickly, that's a high power output. If you go up slowly, bench slowly, that's a low power output, given that you're going the same distance. Right? So you might get the same amount of calories per rep if you go fast or slow, but if you're going fast, you're most likely going to be using your ATP phosphocreatine system. If you're going very slowly, you're probably in the aerobic or the glycolytic pathways. So keep these formulas in mind as you go into physics and as you go into other classes on how to calculate work and power. And in later classes, we'll focus more on what determines how much oxygen you can consume and how much work you can perform.